Hello everyone, welcome back to the batch of excellence where we are learning organic chemistry with respect to your boards, JEE as well as NEET. Well guys, I'm hoping that you all are doing great, and this is Sagar Darvi, your chemistry teacher, and I'm welcoming you to a brand new chapter of organic chemistry which we are starting today, which is nothing but aldehydes, ketones, carboxylic acid and carboxylic acid's derivatives. Well guys, we all are aware that we have been learning this organic chemistry since quite a long time now, and prior to this chapter we have finished two important lengthy chapters, that is haloalkanes and haloarenes, which also included reaction mechanism, and recently we finished alcohol, phenols and ethers. So today we'll be learning another important chapter, and I'm sure this is also one of the bigger chapter in organic chemistry, that is aldehydes, ketones and carboxylic acids. Well guys, let me tell you, if you just go back to all previous year question paper in any competitive examination, be it JEE Main, JEE Advanced or NEET, almost every year you will find at least one question coming from this particular chapter, aldehydes, ketones and carboxylic acid. Collectively we also call it as carbonyl compounds. So guys, it is an important chapter and I want you guys to attend all these lectures of aldehydes, ketones and carboxylic acid and keep solving more and more questions on this. So dear students, let me just show you what are our today's learning objective. So today's session is going to be a little smaller session because it will majorly include the introduction part of aldehydes, ketones, and then we'll be talking about some methods of preparation. Well, so you can see we'll be talking about introduction of carbonyl compounds. In the introduction, we'll also discuss about how the structures of carbonyl group exist. Of course, since you all have studied chemical bonding earlier, I'm sure just by looking at the structure, you will be in a position to tell all the important features of the structure, but we'll be revising that once again over here. Based on its structure, we'll come to know that how polarity is present in that carbonyl compounds, and due to polarity, we'll also discuss about their physical properties such as boiling point and solubilities in water. Guys, once this is done, then we'll be talking about some simple methods of preparation of aldehyde ketones like ozonolysis of alkene. I am sure you all have studied this reaction way back in hydrocarbon when you study chemical reactions of alkene. And then we'll be talking about mercury catalyzed hydration of alkyne, and followed by simple nucleophilic substitution reaction, that is hydrolysis of geminal dihalides. So dear students, let us first talk about something called as carbonyl carbon atom. Well, so when you talk about carbonyl carbon atom, structurally, suppose if I represent carbonyl carbon over here, we represent carbonyl carbon like this. Well, when you look at this carbon, which is doubly bonded connected to oxygen atom, you call it as carbonyl carbon atom. Now remaining two valencies, suppose if I fulfill these remaining two valencies with at least one of the hydrogen atom, so let's say one of the valency I'm satisfying by hydrogen, other could be hydrogen or could be alkyl as well. But if you find at least one hydrogen atom connected to this carbonyl carbon atom, you call such compound as an aldehyde. On the other hand, if I substitute or if I fulfill both the valencies of carbonyl carbon atom either by alkyl or aryl group, then such compound will be referred as ketones. Hence, structurally you find aldehydes are represented as RC double bond OH. So at least one hydrogen atom has to be attached to the carbonyl carbon atom. On the other hand, when both the valencies of carbonyl carbon atom are satisfied by either alkyl or aryl group, or maybe one alkyl and one aryl group, you will still call such compound as ketones. So, because both of this compound contains this carbonyl carbon atom, they are collectively also known as carbonyl compounds. So guys, this is how we define aldehydes and ketones on the basis of their structures. But imagine if you just go back in the previous chapter, which is alcohol, phenols and ether, we studied one very important reactions of alcohol. That was oxidation of alcohol, right everyone? We are not going to include that reaction here since we have studied in detail in alcohol, phenols and ether. But let me just remind you some important points of that reaction. Try to recall, if you take primary alcohol and if you treat those primary alcohol with a mild oxidizing agent such as, let's say, PCC, pyridinium chlorochromate, or PDC, pyridinium dichromate, or if you treat that with Collins reagent, or if you heat with copper. These four being mild oxidizing agent, they convert primary alcohol into aldehyde, right? So such reaction indicates that if primary alcohols are oxidized once using mild oxidizing agent, we get aldehyde. But those aldehyde further upon reaction with some strong oxidizing agent, you will see can be converted to carboxylic acid. Which means primary alcohol periodically can be converted to aldehyde. Further oxidation can give you carboxylic acid as well. Which means, in other words, I can also say that aldehydes are the first oxidation product of primary alcohols. On the other hand, if we substitute primary alcohol with secondary alcohol and treat them with mild or strong oxidizing agent, except hot alkaline KMnO4, because that was drastic condition. So we observe that the secondary alcohols are oxidized to ketone. Again, ketone can be now defined as the first oxidation product of secondary alcohol. So other than the structural features, as in what valencies are connected to carbonyl carbon atom, we can also define aldehydes ketones as the first oxidation product of primary alcohol and secondary alcohol respectively. So this is a basic introduction of aldehydes and ketones. While if you talk about importance of these compounds in our daily life, we see that these compounds comes into our picture. For example, if you talk about let's say some of the artificial flavoring agents such as vanilla, or if you talk about cinnamon flavor. So the organic compound from which these artificial flavors can be obtained in the compounds are again aldehydes and ketones. Like cinnamaldehyde is the one which is found to be having that fragrance of cinnamon, and in several compounds we use it as an artificial flavoring agent. Other than that, even in the medicinal chemistry, to preserve several samples or some of the biological species, we use 40% aqueous solution of formaldehyde, which is called as formalin. So you can see these aldehydes and ketones are found to be having a lot many uses in our daily life as well. Other than that, in several reactions we use these compounds as a solvent. Like you must have observed, even in organic chemistry, acetone is used as a solvent in many reactions. So aldehydes and ketones are such organic compounds which have been found a lot of use in our daily life, and hence studying their chemistry is important for us. So we are learning aldehydes, ketones and carboxylic acid. So far we got introduced to what are aldehydes and ketones. Now we're going to talk about some more important physical properties. So let us first talk about the structure of carbonyl group. Well, probably you might be finding this little complex thing written here. Let's make it simple. Guys, let's say if we have representation of aldehyde, let's say. That's how we represent aldehyde. Now in this aldehyde, if you observe the carbon atom given over here, this carbon atom has 3 sigma bond, 1, 2 and 3, and no lone pair present on the carbon atom. So naturally hybridized state of this carbon atom is sp2. So we can say in aldehydes as well as in ketone, the carbonyl carbon atom exists in sp2 hybridized state. Which means if this carbon is existing in sp2 hybridized state, so out of 3 p orbital of carbon, 2 have been used in hybridization of that carbon atom. 1 p is still left. 1 p is still left there. That p will always remain as a pure p orbital perpendicular to this 3 sp2 hybridized orbitals. Which means other than 3 sigma bond, the pi bond formation that we see here is due to the lateral overlapping of pure p orbital of carbon and oxygen atom. So the sideway or lateral overlapping of pure p orbital of carbon and oxygen is responsible for the formation of this pi bond. So if we try to write down this structure in terms of orbital picture, it looks like this. So do you see here? Now we have taken ketone here. So this is sp2 hybridized carbon having 3 sigma bond obtained by overlapping of sp2 hybridized orbital. Other than that, there is pure p orbital which lies perpendicular to the plane of this sp2 hybridized carbon, and then those p orbital can laterally overlap, resulting in the formation of a pi bond. Well, let me tell you, since we are showing overlapping of the lobe above as well as below the sigma bond, does not mean that there are 2 pi bonds are formed. This means only one of the pi bond formed, but of course for this pi bond to be formed, this overlap has to be a positive overlap. Positive overlap meaning, if you try to recall the chemical bonding concept, we studied that positive overlap is when the two lobes which are compatible in terms of electron density in the phase, if they overlap, then only that overlapping results in the formation of pi bond formation. Meaning, with respect to sign convention, if I write this as plus and minus, and only when this is plus and minus, so the first lobe of carbon which is plus and the first lobe of oxygen which is plus, then only these two can overlap, which will call it as positive overlap, and it will result in the formation of a pi bond. So that is how the lateral overlapping of pure p orbital is resulting in the formation of a pi bond. Now the same structure can also be represented like this, where if you observe carefully, other than the sigma bond, there is electron cloud which is shown above and below the sigma bond. So one of the important feature of pi bond which we have studied is, since pi bond is formed by the lateral or sideway overlapping of pure p orbital, electron density increases above and below the nuclei of two atoms. So this is electron density which has increased above and below the nuclei, or above and below the internuclear axis, you can say. Then question arises, why is this electron cloud shown unsymmetrical? Well, ideally it should have been shown like this. Hold on guys. Ideally it should be like this. You will see electron density is little broader towards oxygen, and you can see little narrow towards carbon atom. Now why is it happening so? See, we have got carbon bonded to oxygen atom, and oxygen is more electronegative than carbon. Since oxygen is more electronegative, it will have a tendency to pull the electron cloud towards itself. So the pi electron cloud which is shared between carbon and oxygen will obviously lean more towards oxygen atom. Hence, the broader part of electron cloud is shown towards oxygen. And if you represent the same thing over here, having mentioned the carbon is in sp2 hybridized states, its geometry is going to be trigonal planar. If geometry is trigonal planar, then the bond angle is going to be 120 degrees. So this is 120 degree bond angle. So that clearly indicates if this molecule is planar. If this molecule is planar, then imagine, since oxygen is more electronegative, it acquired delta minus and carbon acquired delta plus charge. Presence of delta plus charge on the carbon atom indicates that it is electron deficient. So imagine if any incoming nucleophile wants to attack at this carbon atom, but carbon being in sp2 hybridized state has a geometry of planar. So the incoming nucleophile can attack at this deficient carbon either from above the plane or from below the plane, because the molecule is planar. So that's how the structural features of carbonyl compounds tells us that aldehydes and ketone can undergo nucleophilic addition reaction. Well, so that was all about the important features of the structures of carbonyl group. Now let us talk about the boiling point and solubility of this carbonyl compounds. Well, everyone, like we said here, oxygen being more electronegative will acquire delta minus, carbon will acquire delta plus. Naturally, which means if this pi bond has to break, it will always break towards oxygen atom. Imagine if such polarization of bond will take place, we will get carbonyl carbon existing in the form of dipolar ion, right? Pi bond have been broken towards oxygen, where oxygen became electron rich, anionic, and carbon became deficient. This kind of polarity in the bond, that is C plus and O minus, makes this molecule dipole since it has got two poles. Imagine if you have got several such carbonyl compounds or several molecules of a particular carbonyl compound present together, then those adjacent carbonyl compound will always attract each other via the dipole-dipole interaction. Look at this. This is first molecule of some carbonyl compound. This is second molecule. Likewise, you'll have third, fourth, fifth, so on and so forth. So the negative pole of one of the molecule will attract the positive pole of another dipole. Negative pole of the second molecule attract the positive pole of third dipole, so on and so forth. So this kind of attraction will exist between the several dipolar molecule, and such interaction between the two adjacent dipole is what you call it as dipole-dipole interaction. So going back to the basics again, see, whenever we talk about boiling points of compound, what we have been saying always, boiling point of compound depends upon how strongly the molecules are associated with each other. So stronger the intermolecular force of attraction, higher will be its boiling point. Like if molecules are associated with each other via hydrogen bonding as intermolecular forces, so their boiling point is higher, like it happens in alcohol, phenols, or even in carboxylic acid. But imagine if molecules are associated with each other via weaker force of attraction such as van der Waals force of attraction, their boiling point is lower, like how it happens in alkenes. Now carbonyl compounds has a intermediary intermolecular forces, not as strong as like hydrogen bonding, not as weak as like van der Waals forces only. It has got dipole-dipole interaction. Now because of dipole-dipole interaction, they are held quite tightly with each other. Hence they have sufficiently higher boiling point, but of course lesser than the boiling point of compounds which has hydrogen bonding such as alcohol, phenols, or even carboxylic acids. So guys, whatever we mentioned just now, the CO bond is polarized due to higher electronegativity of oxygen atom which exists as a dipolar ion. Now the carbon atom acts as an electrophile because it is deficient, and oxygen atom being electron rich, it acts like a nucleophile. So such molecules, when they are adjacent to each other, they will always be associated with each other via interaction that is called as dipole-dipole interaction, and because of which they are held relatively tightly with each other. So their boiling point is higher than that of compounds such as hydrocarbons, that is alkenes, of comparable molar mass, but lower than that of alcohols or carboxylic acid. That's what we have mentioned here. Thus the boiling points of carbonyl compounds are higher than hydrocarbons and ethers of comparable molar masses, but lower than those of alcohols or carboxylic acids of the comparable molar masses, because in alcohols and carboxylic acid we see there is ability of formation of hydrogen bond. Now further imagine if we have got only carbonyl compound, let us talk about only aldehydes, but differing in their molar masses. Let's say methanol, ethanol, propanol, butanol, pentanol, so on and so forth. Now all of them are going to have a carbonyl carbon. So all of them will be associated via dipole-dipole interaction. So this dipole-dipole interaction is common in all those homologous member of aldehydes. But what is different is the nature of hydrocarbon. Like in ethanol, the value of alkyl is CH3. In propanol, value of alkyl is C2H5. In butanol, it is C3H7, C4H9, so on and so forth. Now, as the number of carbon atom increases, as the nature of alkyl group increases, the molar mass increases, which means the van der Waals force of attraction will also increase in addition to dipole-dipole interaction. So, as the van der Waals force of attraction will increase with the increase in the molar mass, their boiling point will also increase. That's why you will observe that methanol is gas at room temperature, ethanol, that is acetaldehyde, is volatile liquid, and the other higher carbonyl compounds are liquids or solid at a room temperature. That is because with the increase in the molar mass, the van der Waals force of attraction increases. So that was all about boiling point. Now let us talk about solubility. What kind of compounds are found to be soluble in water? Of course, those compounds which are capable of forming intermolecular hydrogen bonding with the water are found to be soluble. Like alcohols are sufficiently soluble in water. Now when you talk about carbonyl compounds such as aldehydes and ketones, again due to polarity, see, we have got delta minus on oxygen. So such delta minus charge which is present on oxygen, which carries of course two lone pair, when brought in contact with a water, since water being dipole, the hydrogen will always have a delta plus charge. When such deficient hydrogen comes in the vicinity of another electronegative atom carrying lone pair, they attract each other via intermolecular hydrogen bonding. Meaning when carbonyl compounds are taken in water, they are also capable of forming intermolecular hydrogen bond, and hence you can say they are moderately soluble in water. They are moderately soluble in water. So water solubility is lower members of carbonyl compounds such as methanol and ethanol and propanol are miscible in water because they can form intermolecular hydrogen bond. But imagine if the value of this alkyl group will keep on increasing. If the value of alkyl group will keep on increasing, alkyl groups are also found to be hydrophobic in nature. Hydrophobic is a water hating tendency which does not allow that compound to get dissolved in water. So as the molar mass of carbonyl compound will keep on increasing, hydrophobic nature will increase, hence solubility will decrease. So higher members will not be found that soluble in water. Further, if you compare the straight chain carbonyl compound and branch chain carbonyl compound, as the branching will increase, molecule will become more and more compact. As molecule becomes more and more compact, its surface area will decrease. If surface area decreases, in a way its hydrophobic character also decreases. Hence solubility of branch chain carbonyl compound will be more than the normal chain carbonyl compounds. That's what we are talking here. First point, but the solubility of carbonyl compound decreases with the increase in the carbon atom because non-polar part meaning hydrophobic part increases. Further, branch carbonyl compound, as the branching increases, surface area decreases. So solubility will increase. However, branch carbonyl compounds are found to be more soluble in water than the straight chain carbonyl compound, since upon branching the surface area decreases and solubility increases. Right everyone? So that was all about the solubility. Now further when you talk about a compounds with respect to their solubility, you will find that the compound which are having further higher branching, as we mentioned, they will have lesser surface area and solubility is going to get increased, right? So if you talk about carbonyl compounds with the higher molar masses, because in case of higher molar masses the non-polar part is increasing, which means their solubility in water is going to get decreased, meaning in other words they will be more soluble in non-polar solvent such as organic solvent like benzene or ether or methanol or chloroform. So all carbonyl compounds are fairly soluble in organic solvent. It is because the non-polar part which is present in the molecules, that is nothing but the alkyl group present. Alright guys, so that was all about the solubilities and the boiling point of carbonyl compounds. Well guys, based on this, now let's have a look at some questions here. Oh, before question, one more property we'll discuss about the comparison of bond polarity of carbonyl carbon and carbon carbon double bond. Well guys, when we studied reactions of alkene, for example, let me just remind you some important reactions such as acid catalyzed hydration or oxymercuration demercuration, or for that matter even hydroboration oxidation, right? If you try to recall in this reaction, let's say acid catalyzed hydration, so the H plus ions which are present in the reaction mixture were attacked by the pi bond of alkene. So alkene acts like a nucleophile. It is an electron rich center which attacks at electrophile. So alkene undergoes electrophilic addition reaction. Now why it happens so? It happens so because across carbon-carbon double bond, the pi electron density which is present is symmetrically distributed between the two atoms, because both the atoms are of identical electronegativities. On the other hand, in case of carbonyl carbon, O being more electronegative, it acquires delta minus and carbon acquires delta plus. This development of polarity across carbonyl carbon atom makes this carbon electron deficient. Hence it acts like an electrophile, and oxygen being electron rich acts like a nucleophile. Because of deficiency of carbonyl carbon atom, nucleophiles can attack at this carbonyl carbon atom slowly in a rate determining step. So because rate determining steps of a reactions of carbonyl compound involves attack of nucleophile, we say carbonyl compound shows their characteristics reaction called as nucleophilic addition reactions. Unlike alkene, we shows electrophilic addition reaction because this pi bond can only act like a source of electron by which it can attack at electrophile only. But carbonyl compound can also invite attack of nucleophile. That's why carbonyl compound shows characteristics reaction called as nucleophilic addition, and alkene shows their characteristics reaction such as electrophilic addition reaction. So that is a basic difference in the reactivity of two compounds, that is alkene and carbonyl carbon. So guys, so far what we have studied, we'll just revise that and then we will see one question on the boiling point of compounds. So we started our discussion with what are aldehydes and ketones, how do we define them structurally, how do we define them on the basis of the oxidation product of alcohol. Then we talked about some of the physical properties such as boiling point, how dipole-dipole interaction is responsible for relatively higher boiling point of aldehydes and ketones. Further, we talked about solubility of carbonyl compounds in water as well as in nonpolar solvent. So in water, due to presence of dipolar nature, they form hydrogen bond with water, but of course the solubility is moderate. As the number of carbon atom in alkyl group will increase, its solubility will decrease. Hence we say due to that non-polar nature of alkyl group present to the carbonyl carbon atom, they are found to be fairly soluble in organic solvents such as benzene, methanol, so on and so forth. So guys, finally we then talked about how alkene shows their characteristics reaction electrophilic addition, but carbonyl compound shows their characteristics reaction of nucleophilic addition due to the polarization of carbonyl carbon atom. And now we will be discussing two questions here. Well, on your screen I want you guys to have a look at this question. Everyone, give the decreasing order of boiling points of following compounds. Okay. Butanol, butane 1-ol, diethyl ether and pentane are the four compounds given to us. Come on everyone, I want you guys to give a thought to it. Okay, give the decreasing order of boiling point for the compounds. First is butanol. 1, 2, 3, 4. Second is butane 1-ol. 1, 2, 3, 4. Third is diethyl ether. Fourth is pentane. Well, nothing mentioned, we assume it to be in pentane. 1, 2, 3, 4 and 5. Right? Now we have to find out the order of boiling point. Like we have been saying, order of boiling point depends upon how strongly the molecule of that compounds are associated with each other. So we always look for intensity of the intermolecular forces. If you look at carbonyl carbon, you will see there is a presence of delta plus and delta minus. So several molecules of butanol can be associated with each other via dipole-dipole interaction. So interaction which is present here is a dipole-dipole interaction. In case of alcohol, there is a presence of oxygen-hydrogen bond. So molecules of alcohols will be associated with each other via hydrogen bond. So here interaction is going to be hydrogen bonding. Here interaction is going to be dipole interaction. Of course, other than dipole, because of presence of this alkyl loop, there will be van der Waals forces also. Here also, other than functional loop OH, which will show hydrogen bonding, due to presence of nature of hydrocarbon, there will be van der Waals forces also. In case of ether, well, oxygen is connected to carbon atom which carries delta minus and carbon carries delta plus. But this polarization is not that strong polarization as much it is present in case of carbon bonded to oxygen via double bond. So dipole-dipole interaction will be stronger here. So you can say strong dipole-dipole interaction plus van der Waals, and here you can say relatively weak dipole interaction, and in case of N-pentane it is just van der Waals force of attraction. So clearly we can see here hydrogen bonding will associate the molecule of alcohol more strongly, so their boiling point is going to be highest. So 2 is going to be highest boiling point, followed by stronger dipole-dipole interaction present in 1. So the second highest boiling point will be for aldehyde, followed by weak dipole, that is in number 3, and the least boiling point will be of compound which is having a weaker intermolecular forces, that is pentane, that is number 4. So this is going to be the order of decreasing order of boiling points of compounds given in question A. Now if you talk about question B, in question B the first one given is propan-2-ol. So again here there is intermolecular hydrogen bonding coming into picture other than van der Waals. Number 2 which they have given us is propan-2-one. Propan-2-one, guys, this is nothing but acetone, right? Dimethyl ketone. And then we have got 2-methyl propene. Third is 2-methyl propene. Let's say that's propene, carrying methyl at number 2. So yet again you can see here, in case of first molecule there is ability to form intermolecular hydrogen bond. In second, molecule can be associated with each other via dipole-dipole interaction. In third, probably will have the major forces attracting the molecules of this alkene are going to be van der Waals forces. So stronger the intermolecular forces, stronger the association, higher the boiling point. So boiling point of alcohol will be the highest, followed by number 2, followed by number 3, that is propene, of course compound having comparable molar masses. So dear students, if they give you any such question where there have been several compounds have been given, you just have to identify which molecule is going to have hydrogen bonding as their ability to be associated as intermolecular forces. So generally you will see carboxylic acid will have relatively higher boiling point, followed by alcohol, and then carbonyl compounds, and then you may have compounds such as alkyl halide or ether or alkenes. That is going to be the decreasing order of their ability to form or to be associated via intermolecular forces. Alright everyone, so that was the introduction part of aldehydes and ketones. Well, all these things probably are more helpful for you all, keeping the board examination point of view. But generally, if you see in the competitive exam, the questions would be coming, majority of question comes from the reaction part. So guys, we are starting straight away with the methods of preparation of aldehydes and ketones. First, a very important reaction. Probably you guys studied this reaction in standard 11th in the chapter of hydrocarbon. In an alkene, as a chemical reactions of alkene called as ozonolysis of alkene. We are going to see this reaction in detail. Firstly, when you talk about ozonolysis, the term ozonolysis stands for lysis, meaning breaking of a double bond using ozone. So you call it as ozonolysis of alkene. So such ozonolysis of alkene is generally done by addition of ozone in presence of solvents such as dichloromethane. So let's say we have got CH2Cl2. So this ozone gets added across carbon-carbon double bond via formation of mole ozonide, which eventually result in the formation of ozonide. Now how it happens, let's see that in detail. Well, so let's say we have got an alkene. R, C, R, double bond, R dash, H, and treating this with ozone. If we draw the Lewis structure of ozone, this is how ozone looks like. And okay guys, now look here. The central oxygen of an ozone is carrying positive charge. So let's say to neutralize that positive charge and to bring back the divalency of oxygen, let's say this pi bond breaks here. As a result of pi bond breaks here, this oxygen is going to become deficient. Deficient meaning this oxygen will now behave like an electrophile. Now since we are allowing such ozone to react with an alkene, and having said few minutes back, comparison between C double bond O and C double bond C, alkene's pi bond being symmetrically distributed between the two identical atom carbon, alkene always act like a source of electron. It is always electron rich, hence act like a nucleophile. Hence if you remember in GOC, we refer alkene as a pi bonded nucleophiles. So the moment this becomes deficient oxygen atom, this pi bond will break towards one of the carbon, making it rich, which will then attack at the deficient carbon, deficient oxygen. But because this pi bond is breaking towards carbon, the other carbon is becoming deficient, which will be now attacked by this electron rich oxygen atom. That's how the cyclic molecule will be formed. That cyclic molecule we refer it as mole ozonide. So the mole ozonide I'm writing here. Now we have got RCR bonded to R dash and H, and the mole ozonide formation can be represented like this: O carrying 2 lone pair, single bond O will be again carrying 2 lone pair. One was already there, pi bond came to neutralize positive charge, so we got one more lone pair, and bonded to yet another oxygen which is also carrying 2 lone pair, bonded to carbon. This is what we refer it as mole ozonide. This mole ozonide being unstable itself dissociate, or rather you can say decomposes to form ozonide. Now how the formation of this takes place, let's see that first. Look, let's say this pi bond broke over here, making this oxygen anionic. Alright, now this carbon-carbon bond, let's say, hold on everyone. Hold on guys, this pi bond broke over O, making it O minus. This bond broke over carbon oxygen, So you can see now this development of carbon-oxygen double bond. This carbon is becoming deficient, so the lone pair will delocalize. So what we have got now? If I write this part, RCR double bond O. C double bond O carrying 2R. Alright. Now this bond broken over O, making it O minus. Let's say this is O minus. O minus meaning it has got 3 lone pair, which is further bonded to another oxygen carrying 2 lone pair. Now only 1 lone pair left ideally, and doubly bonded further connected to another carbon, carrying R dash and H, and this O is carrying positive charge. Right, everyone? See, mole ozonide which is formed itself decompose. So this bond between carbon and carbon heterolytically broken towards O, making carbon-oxygen double bond. This single bond broke over O, making it O minus. Because this carbon is becoming deficient, lone pair delocalized to give you pi bond over here. Now see what happens. In order to neutralize this positive charge, this pi bond will always have a tendency to break towards O. Because of which this carbon is always going to be deficient, so the lone pair of oxygen will attack here. So this O will carry positive charge because it is sharing electron pair. So this bond will break, making carbon deficient. As soon as this becomes deficient, the anionic oxygen will attack at this. This all steps will take place simultaneously. Pi bond will break towards O to neutralize positive charge, making carbon deficient. So lone pair will attack. O will carry positive charge. So pi bond will break towards O to neutralize that O, making carbon deficient. So anionic oxygen is attacking at the carbon. So we finally got our desired product, carbon carrying 2 alkyl group. Singly bonded connected to oxygen. The carbon further carrying R dash and H. And it is connected to O through new single bond, and between oxygen and carbon again only single bond left. And this is what we are referring it as ozonide. So everyone, an alkene upon reaction with ozone in presence of dichloromethane first produces mole ozonide, which itself decomposes and rearranges to form ozonide. So here you can see the rearrangement took place. To form ozonide. Now once the ozonide is formed, this ozonide can be further broken under either oxidative condition or reductive condition, is what you are referring it as lysis, ozonolysis. So the ozonide which is formed now will be further broken either under oxidative condition or under reductive condition. So we are going to refer it as reductive ozonolysis or oxidative ozonolysis. So generally reductive ozonolysis condition that you see will be carried out using zinc water, or sometime you might say zinc in acetic acid. Zinc in acetic acid. Acetic acid symbolically also written as ACOH, that is acetyl group carrying OH, or zinc in water, or you may see dimethyl sulfide. So upon arrow, if you ever observe that the ozonide is written with zinc in water or zinc in acetic acid or dimethyl sulfide, which means you have to understand the condition is going to be reductive ozonolysis. We'll see the importance of how reductive ozonolysis gives different product than that of oxidative. And if we see on arrow, if they mention ozonolysis, that is O3, and followed by H2O2 or Ag2O, meaning they're talking about you're carrying out oxidative ozonolysis. So when you carry out reductive ozonolysis, what happens? Simply to understand the product, what you guys have to do, I'm carrying out homolytic breaking of C bond O, C single bond O. Further, I'm also carrying out homolytic fission of this O bond O. Alright. Same thing I'm doing from the other side as well. other side, as in I'm carrying out homolytic fission of this C double bond O as well. And this is for your understanding, as well as this O single bond O. Now, assuming that this is homolytic fission, guys, this carbon will have one electron from this bond, this O will have one electron from this bond. Now, those two odd electrons will be shared with each other to give you C double bond O. So, we are going to get RRC double bond O, RRC double bond O. On the other side, this C carrying odd electron, O carrying odd electron will give you R dash C double bond OH. So, the two product that we are getting here from the left hand side is R C double bond O and R, right everyone? And on the other side, R dash C double bond OH, which is an aldehyde. R dash C double bond O and H. So this is ketone and that is aldehyde. So one of the product obtained is ketone and the other product obtained here is aldehyde. Similarly, if you carry out oxidative ozonolysis, again the bond breaking will take place exactly in the similar manner. So the left hand side part is again forming ketone and right side part, let's say as of now, we can see it is forming aldehyde. So let me first write down the product which we expect. So R C double bond O and R, right everyone? R C double bond OR, that is ketone. R dash C double bond OH, that is aldehyde. So we have ketone plus O double bond C R dash and H C double bond OH, that is aldehyde. Well guys, now whether or not our product is going to remain aldehyde or will it be further oxidized? See, now we got product aldehyde in the second case also, but in reality whether our product is going to remain only as aldehyde or is it going to get further oxidized, that depends upon the conditions. So if you observe, the condition mentioned are oxidative ozonolysis, and aldehydes are such compound which contain hydrogen atom, right? By definition, at least one hydrogen must be connected to carbonyl carbon. Such hydrogen which is connected to carbonyl carbon atom is known as oxidizable H. Oxidizable H are those H's which can be oxidized provided conditions are oxidative enough. So because our conditions are oxidative and they're oxidative enough to oxidize this H, now what happens? Your product will not be just aldehyde, this will undergo oxidation, that is addition of oxygen. When addition of oxygen took place, this is no more aldehyde, this is RC double bond OH, which is nothing but carboxylic acids. So everyone, under oxidative conditions, if you find one of your product is going to be an aldehyde, it will be further oxidized to acid. In case of ketone, at carbonyl carbon, both the valencies are always fulfilled by alkyl groups. There is no oxidizable hydrogen present. Hence, even in oxidative condition, ketones remains ketone. In case of reductive condition, ketone anyways does not have oxidizable S, so it is going to remain ketone. And even aldehyde remains aldehyde as your product because the conditions are reductive. Conclusion: an alkene, when subjected to ozonolysis in presence of CH2Cl2 via mole ozonide followed by rearrangement, produces ozonide. This ozonide is further broken or decomposed either under reductive condition or oxidative. Upon reductive condition, if your product is ketone, it will remain ketone, and if your product is aldehyde, it will still remain aldehyde because conditions are reductive. But if conditions are oxidative, then ketone will remain ketone only. But if any compound is going to form an aldehyde, it will be oxidized to carboxylic acid. And imagine if we would have had a terminal H, terminal alkene I mean. Imagine if R dash would have also been H. If R dash would have been H, then it would have been HC double bond OH. So here we would have got formaldehyde, HC double bond OH as a reductive condition. But in oxidative condition, both would have been H, meaning both would have got oxidized. Like this H got oxidized. Even H here would have got oxidized. Meaning that compound would have given you unstable diol, and which would have decomposed further to give you CO2 and H2O. We will see one such example. Point here is, if your alkene is terminal alkene and if conditions are oxidative, you are not going to get carboxylic acid, you will get CO2 and H2O. For example, let's say well guys, let's say we have been given isobutene. And if they are saying on arrow, let's say we have got O3 in presence of CH2Cl2, and second, followed by, let's say, they say the condition mentioned is H2O2. First of all, the moment you see that ozone is mentioned, which means they're talking about ozonolysis, and H2O2 meaning they're talking about oxidative ozonolysis. So how are we going to write down our product? We don't have to write down the entire mechanism. Simply what we can do, wherever you see double bond, break down that bond. Add oxygens on either side. See what the left hand side part is forming? CH3, C double bond or CH3, that is acetone. And the right hand side part is forming HC double bond OH, meaning as of now formaldehyde, let's say. So left hand side is forming dimethyl ketone, and the right hand side part as of now O double bond C, single bond H, single bond H. Right? Now because these two H's are connected to carbonyl carbon, they are oxidizable, so they will undergo oxidation, so you'll get OH. Now see, at the same carbon 2OH being unstable, it will further immediately eliminate water molecule. So the bond between O and H, which was here, will shift here. So this is eventually going to give us product as C double bond O double bond O, meaning CO2 and H2O. CO2 and H2O. Conclusion: if we have terminal alkene and if conditions are oxidative ozonolysis, then we are not going to get formic acid, we'll be getting CO2 and H2O. And let me tell you, these oxidative conditions, just like H2O2 or Ag2O, are also found to be shown by hot alkaline KMNO4 or acidified dichromate when you treat them with the alkene. Well, we are not discussing those reactions as of now. As of now, that is how ozonolysis of alkene is carried out under reductive or oxidative conditions, and this is the simple trick you can apply. Let's see some more question to have better idea of questions, better idea of concept. Let's say we have been given this alkene, ozonolysis, zinc in water, indicate it is reductive condition. H2O2 is oxidative. So what are we going to do? We will break down the bond. Add oxygens on either side. As long as it is reductive, aldehyde will remain aldehyde. So CH3, this should be CH3. This should also be CH3. So CH3, CH2, CH double bond O, propionaldehyde. And right hand side is CH3, C double bond O, CH2, meaning acetone. So two products are propionaldehyde plus acetone. Whereas if you carry out oxidation, meaning oxidative ozonolysis, then ketone will still remain ketone. But the aldehyde which contain oxidizable H will get oxidized, and that's how it's going to be COOH. Meaning here we will be getting CH3, CH2, C double bond O, and now this got oxidized to give you COOH. Propionic acid and the ketone, since does not contain any oxidizable H, it will still remain ketone. So we will be getting O double bond C and CH3. Alright everyone, let us apply that to another example. You can see dimethyl sulfide indicate that this is reductive condition and Ag2O is oxidative. Carbon-carbon double bond will break this bond. Add oxygens on either side. So left hand side part is again propionaldehyde, right hand side part is acetaldehyde, CH3CH double bond O. So under reductive condition, two products are first is acetaldehyde plus the second one is acetaldehyde. But if we carry out oxidative ozonolysis, both contain oxidizable H's, so those will be oxidized, which means instead of propionaldehyde, we will now be getting C double bond O, and now this got oxidized to give you COOH, and the other one we will be getting CH3 C double bond O and OH, that is acetic acid. Alright guys, let's take one more example of cyclic structure. Let's say we have been given cyclohexene, let's say. Okay, let's take methyl cyclohexene. Alright, and two conditions we will take. One is oxidative, other is reductive. So ozonolysis in presence of, let's say, zinc in acetic acid. And here, let's say hydrogen peroxide. Okay, everyone. Now, we have been given alkene. First, we need to understand that we have to break down this carbon-carbon double bond. But here, I can only see 3 bonds as of now, 1, 2 and 3. So, fourth by default has to be hydrogen. So, mention that hydrogen. So, 2 carbon which are carrying the double bond, make sure that all the valencies are visible, whether they are methyl or hydrogen or any other group. So, that's what we did here. And now, ozonolysis, so we'll break down the double bond, add oxygens on either side. So the bond where you have broken, above that you will find it is C double bond O, that is ketonic group, and your C double bond OH, that is aldehyde group. So under reductive conditions, the product obtained would be, if we start from this aldehydic, for simplification, let me number this as 1, 2, 3, 4, 5, 6 and 7. So we'll be getting 7 carbons chain. 1, 2, 3. Let's call this is 1, 2, 3, 4, 5, 6 and 7. At first carbon it is aldehyde. So C double bond OH. At 6 carbon it is ketone. First, second, third, fourth, fifth, 6. Right everyone? See, if you do numbering, it will be easy to understand. 1, 2, 3, 4, 5, 6, 7. 6 oxoheptanyl is the product obtained. So aldehyde is still remaining aldehyde because the condition is reductive, right? So this was the reductive condition. The second condition mentioned is oxidative, meaning now wherever you see oxidizable H, that H has to be oxidized. So this H which is connected to carbonyl carbon is oxidizable, so we will oxidize that. So hydrogen peroxide will oxidize it. Again the chain will be still of 7 carbon only. So 1, 2, 3, 4, 5, 6, 7. Ketone does not carry any oxidizable, so will remain ketone. But now this H is oxidizable, and being oxidizable, you will write it as COOH. So the product will now change. It is 1, 2, 3, 4, 5, 6 and 7. 6 oxoheptanoic acid or 6 ketoheptanoic acid. That is how cyclic structure can also be ozonolized can be subjected to ozonolysis under reductive or oxidative condition. So guys, that was all about the ozonolysis of alkene, which also helps for the formation of aldehydes and ketones. In fact, the same reaction can also be considered as one of the method of preparation of carboxylic acid, provided conditions are oxidative. Right, everyone? Well, after this, another important reaction from yet another hydrocarbon, which is alkyne, and alkyne can be hydrated in presence of mercury as a catalyst. So we call it as mercury catalyzed hydration of alkyne. The mercury catalyzed hydration of alkyne is also known as Kucherov's reaction. So yes, you can see we have got alkyne, let's say acetylene. We are hydrolyzing it, or we are rather hydrating it in presence of acid catalyst, which is also catalyzed by addition of 1% HgSO4. So whenever you see you have got an alkyne to which water will be added in presence of dilute H2SO4 like 40% H2SO4 and also catalyzed by 1% HgSO4, it is mercury catalyzed hydration of alkyne, which gives you either enols of aldehydes or ketone, which will tautomerize to give you corresponding aldehydes or ketones. We will see that for sure. Well, some important point that we all need to understand first. Look, when we studied ACH, acid catalyzed hydration of alkene, we simply took alkene and we added water in presence of H2SO4 or H3PO4. So the pi bond of alkene is to attack at either H plus of H2SO4 or H3PO4 to form carbocation. And hence ACH, important feature were it involves formation of carbocation followed by attack of water. Now imagine if the same process happens in case of alkyne. Let's say one of the pi bond breaks, which attacks at H plus. So if one of the pi bond is going to attack at H plus, meaning one of the two carbon will become cationic, carrying double bond. If one of the pi bond attack at H plus, any one of the two carbon will become cationic, carrying double bond. So positive charge present at the doubly bonded carbon is highly unstable. Hence, the breaking of a pi bond of alkyne or catalyzing the alkyne or breaking the pi bond using just H plus ions becomes difficult, because after attacking the pi bond at H plus, the corresponding carbocation is not stable like it happens in case of alkene. Hence, carrying out hydration of alkyne is always difficult as compared to that of alkene. Hence, we need a special catalyst which will still carry out the breaking of pi bond of alkene, but not via carbocation formation. That catalyst which we use is HgSO4, where Hg exists as Hg plus 2. Right, everyone? So, ideally, we are not supposed to study any mechanism here. So, ideally, if you just see pi bond of alkyne attack at Hg plus 2 to form cyclic mercurinium ion, and then water attacks to form corresponding enol. And we are not supposed to study the mechanism as far as the guideline of our syllabus is concerned. But what I want you to understand, whenever you will carry out hydration in presence of 40% H2SO4 catalyzed by 1% HgSO4. Now in this case, alkyne is symmetrical, so you can add water anyways. Let's say I added H plus here and OH minus here, let's say. So we will be getting a compound as CH2. Right, you had CH, one more H plus added, triple bond will become double bond, carrying carbon with one hydrogen connected to OH. So now we have got CHOH. CH and OH. If you observe this compound, it is nothing but enol. So such enol will immediately undergo tautomerization. This will be tautomerized. So upon tautomerization, the sigma bond will break here further. So carbon will become pentavalent. This pi bond will go back to carbon, making it electron rich. This rich carbon will then accept H plus either from the one which was lost from here or H plus from the solvent, wherever. So see, what are we going to get? CH2 after accepting H plus will become CH3. Double bond upon breaking became single bond. CH double bond O. CH double bond O. This product is nothing but acetaldehyde. So ethine or acetylene upon mercury catalyzed hydration produces enol, which tautomerizes to give you aldehyde. Now see, wherever this OH attacks, wherever this OH is attacking, that part is becoming aldehyde group. So because now we had a H here, we got formation of aldehyde. Imagine if this would have been R, we would have got ketone, isn't it? So formation of aldehyde is observed only in case of acetylene. Imagine if you take any other propyne. If you take any other propyne, you're going to get different product. For example, if you take any other alkyne, we are going to get ketone as the product. So let's say now we have got, as an example, CH3, C triple bond, CH. And now we are saying that we are carrying out hydration of such alkyne in presence of 40% H2SO4 and 1% HgSO4. So what will happen, like I said, when we are adding water catalyzed by mercury, always this reaction should follow Markovnikov addition. Now why it happens so is, ideally if you just go through mechanism, pi bond attacks at Hg plus 2 to give you cyclic mercurinium ion, then the negative part of the reaction will always attack at that carbon which is more substituted, or the carbon which resemble to more stable carbocation. So naturally the carbon to which substituent is present will be more stabilized, will be resembling to more stabilized carbocation. Hence the negative part of the water, that is OH minus, should always be added to the substituted carbon of a triple bond. So OH will be added to the carbon carrying methyl, triple bond will become double bond, and this CH will be attached to H, which means the product obtained will be CH3, C, which will be carrying OH, triple bond will become double bond, and this carbon will be carrying one more H from the water. So see, now we have got enol, but the OH is not at the terminal carbon like it was here. As long as OH is present at the terminal carbon, you are always going to get an aldehyde. Now since it is present at the non-terminal carbon, and other than ethine, for any other alkyne, you will always find that OH will be attached to the non-terminal carbon of triple bond. That's what happened here. And now this will tautomerize. This will be tautomerized. How do we write tautomerized? Tautomeric form. The protic H is lost as a H plus, so the sigma bond shifts here towards carbon, making this carbon pentavalent. 1, 2, 3, 4 bonds are already there. This will become fifth bond. So the pi bond will break towards one of the carbon. That anionic carbon will now either accept H plus from here or from the solvent. Let's say it accepted from here. So what are we getting? CH3, C double bond O, single bond, CH3. So everyone, the product formed is CH3, C double bond O, and this is CH3 again. So the product obtained is dimethyl ketone. Commercially, we also call it as acetone. Alright everyone, conclusion. If they give you any alkyne, only in case of acetylene, because both carbons are terminal, when you will add water, OH is going to get attached to either of the carbon, which is always going to be terminal. And when OH is present at terminal carbon, upon tautomerization, we are going to get aldehyde. But if you take any other alkyne, then if that alkyne is terminal alkyne, but it is going to be unsymmetrical terminal alkyne like this, then the OH part of water will always attack at the substituted carbon, meaning at the non-terminal carbon. If OH is present to non-terminal carbon, upon tautomerization, it is always going to give you ketone. Now look, you might be thinking, what if we have got non-terminal alkyne, meaning even this is substituted by CH3. Now as long as this alkyne is symmetrical, then addition of water is going to give you same product anyways. But imagine if triple bond is present in the carbon chain such that the molecule is not symmetrical, then the possibility of formation of ketone will be by attack of OH at any of those two carbon which are carrying triple bond to give you two different ketones. But again, such reaction is not preferred because it will result in the formation of mixture of ketone. Hence, generally you will find the reaction will be used for the preparation of ketone from the terminal alkyne, which are going to be asymmetric. In case of symmetric, we are going to get the identical product, and in case of little correction guys, I mean the terminal alkynes where the triple bond present in such a way that the carbon which is substituted will always form a ketone, and if it is present where triple bond is present in between the carbon chain, then such alkyne will not be hydrated because it is going to give you mixture of ketones. So that's how aldehydes and ketones can be obtained by addition of water catalyzed by a mercury. Now one final and simple reaction everyone here is by hydrolysis of geminal dihalides. Well, when you talk about dihalides, depending upon two halogen atoms present either on the same carbon or on the adjacent carbon, we classify them as geminal dihalides and vicinal dihalide respectively. So when both the halogen atoms are present on the same carbon, we call it as geminal dihalide, and when they are present on the adjacent carbon, we call it as vicinal dihalides. So like here, let's say we have got a terminal geminal dihalide. You can see here both halogen present on the same carbon, so it is definitely geminal dihalide. But the carbon to which two chlorines are present is primary, meaning it is terminal carbon, so you call it as terminal geminal dihalide. Now let's say we took excess of KOH and we hydrolyzed it. So let's say two equivalent of KOH are reacting with, hold on guys, two equivalent of KOH are reacting with this geminal dihalide. So because it is primary alkyl halide, with KOH it will undergo nucleophilic substitution and both the chlorines will be substituted by OH. If that happens, as a result of nucleophilic substitution, we will be getting CH3 CH, CH2 CH carrying two chlorine, both being substituted by OH. Yet again, two OHs at the same carbon makes it highly unstable. Being highly unstable, it will eliminate a water molecule. So let's say we are eliminating water from here. Sigma bond will shift back here to give you C double bond O. So the product obtained will be CH3 C double bond OH. So we will be getting acetaldehyde. That is acetaldehyde. Now everyone just look at this H. This H is the same H which was present at the terminal carbon, that is primary carbon. Imagine if we substitute this hydrogen with methyl. So this H will also be methyl. this H will also be methyl. In that case, we won't get aldehyde. We would rather get ketone. So we got ketone when we substituted this H with CH3, meaning now this carbon was no more terminal, it was non-terminal carbon. So when you have dihalide present at non-terminal carbon like this, see, two halogen present at the secondary carbon atom, it is non-terminal carbon. If you carry out hydrolysis using, let's say, 2 aqueous KOH, both the chlorine will be substituted by OH. So we will again get diol just like this. But now the two OHs will be at non-terminal carbon. If I write it down, let's say CH3C. Now this two chlorine which were there and the third methyl I'm putting down here. So that representation of product will become easier. And two chlorines I'm substituting by OHs. So this is first OH and this is second OH. Since two OHs are at the same carbon, this is geminal diol, and diol being highly unstable will eliminate water. So let's say water is eliminated. Sigma bond will shift back here between carbon and oxygen to form double bond. So we will get CH3C double bond O CH3. So the product obtained here is CH3C double bond O CH3. CH3C double bond O CH3 dimethyl ketone. As we said earlier, we commercially call it as acetone. Conclusion: terminal geminal dihalide, or you can call it as primary geminal dihalide, upon alkaline hydrolysis will give you aldehydes, whereas non-terminal geminal dihalide or secondary geminal dihalide on alkaline hydrolysis will always result in the formation of ketone. So dear student, as far as methods of preparation of aldehydes and ketones are concerned, we covered 3 reactions. Okay. First 2 reactions were preparation of aldehydes and ketones from hydrocarbons. So we took alkene first, we subjected them to ozonolysis. Ozonolysis can be performed either under oxidative condition or reductive condition. As long as conditions are reductive, upon breaking the pi bond, whatever product you get, whether aldehydes or ketone, will remain aldehydes and ketones only. Under oxidative condition, ketones will remain as ketone only, but the aldehydes which are formed since contain oxidizable H will be converted to carboxylic acid. And if your alkene is terminal alkene, of course we are going to get CH2 group, which is nothing but going to get converted to formaldehyde. But being condition oxidative, that formaldehyde will be converted to CO2 and H2O. So terminal alkene case, you have to be a little careful. Then the second hydrocarbon from which we prepared aldehydes and ketones are the mercury catalyzed hydration of alkyne. As long as it is ethane, you are going to get aldehyde. For any other terminal alkyne, you will be getting ketone, in which OH always should be connected to the substituted carbon. That's how you are going to get the ketonic group. Right, everyone? And finally, we also prepared the aldehydes and ketones by alkaline hydrolysis of geminal dihalide. If dihalide is primary or terminal geminal dihalide, the product will be always aldehyde. And if your geminal dihalide is non-terminal or secondary, the product is going to be ketone. So in the first part of our today's lecture, we talked about introduction of aldehydes and ketone, its structures, its bond polarity, and how it contributes towards boiling point as well as solubility. Then we talked about the comparison of C double bond O and C double bond C, how alkene gives you electrophilic addition reaction as their characteristics reaction, and how ketone gives you nucleophilic addition reaction as their characteristics reaction, followed by some methods of preparation. So guys, that is it from our today's class, and we'll stop here. And in the next class, we'll be discussing about some more important methods of preparation of aldehydes and ketones. So I'll see you there very, very soon. Thank you so much, everyone. Take care.